Radar Parameter Analysis and Measurements Part 2. Welcome back to Part 2 of our webinar, Radar Parameter Analysis and Measurements. Part 2 of the webinar is introducing how to use the Anritsu MX28005A IQ Signal Master for trimming, replaying, and conversion of the previously gained IQ data. Besides, we are showing the extended capabilities of XCOM SpectreX software for replay, signal autocorrelation, and automated pulse analysis. Finally, we are discussing the RUBIDIUM signal generator for pulse signal generation, and we are demonstrating the capabilities of the Anritsu MG3710E vector signal generator, as well as the Anapico app VSG for physical retransmission of IQ baseband data. IQ capture and post-processing with MX28005 Alpha IQ Signal Master. How to record the signal? Recording in this sense means the conversion of a time record length or a continuous time series into baseband data, the so-called I and Q. MS2090A as well as MS2720XA and MX28XXA are coming into the play here. All these instruments allow IQ baseband recording. The MS2090 Alpha platform, up to a frequency of 54 GHz without any kind of external mixer, and a maximum IQ bandwidth of 110 MHz. The MS28XXA platform goes up to 44 GHz and in different versions up to 1000 MHz IQ bandwidth. This is the MS2850 Alpha. Finally, the youngest platform, the faceless spectrum analyzer MS272XOA, offers the same performance as the MS2090A handheld spectrum analyzer. So, what do we need for physical retransmission? Usually on the same as previously discussed, but also probably on different frequencies. First of all, there is the vector signal generator MG3710E. Different frequency versions of 2.7, 4, and 6 GHz qualifies this unit as a working horse of any kind of cellular-based applications. It's worth mentioning that this device offers two physical, independent RF channels together with a deep waveform memory of 1024 megasamples per channel and a maximum IQ bandwidth of 120 MHz. The app VSG platform from our partner Anritsu is the solution for aerospace and defense applications. Different frequency models, 512 megasamples waveform memory, and the maximum modulation bandwidth of 400 MHz allows for manifold application up to the satellite communication environment. Finally, there's also a rack mount version of the app VSG available. The app VSG X multi-channel vector signal generator is the corresponding multi-channel product series. Up to 4 channels per device is possible. Phase coherent switching guarantees deterministic and reducible phase relationships between multiple individual channels across multiple individual units. The phase coherent switching mode also enables synchronous playback of IQ waveforms on multiple channels and multiple devices. Up to now, this was the hardware-based side of IQ capture and replay. Usually, the gained IQ baseband data occupies large amounts of memory, and this is putting a lot of stress on the user while handling such large files. If your system is currently, for example, set to a FAT32 partition, you will have no problem transferring files if their size does not exceed 4 GB. However, when operating larger files, you run into a specific error. Instead of splitting your files every time, you could set your files system to NTFS, which will allow you to copy files with a maximum size of 16 TB. But for sure, you will need a piece of software that administers your captures, allows for editing, file replay, and data format conversion for the use together with the vector signal generator. The answer to this is the Anritsu MX2800005A IQ Signal Master software platform. This toolbox allows for all of the tasks mentioned. You can browse and administer files. You can remote control your instrument and conveniently initiate captures also from remote, or even automatically from up to 4 units in parallel and also GPS assisted. You can convert very flexible between different IQ data formats, and you can operate even large files conveniently. Together with option 128 on the hardware, you can perform even vector signal analysis on the gained IQ data. Here we see the main graphical user interface of the remote control and IQ capture tool. Let me explain briefly the handling with the next couple of slides. So now let's have a look more into the details. As said beforehand, you can take time records, or you can stream baseband data from the device into the software or your own application. There are manifold IQ bandwidths available, from minimum 36 kHz up to maximum 110 MHz. Bit depth varies from integer 8 up to floating point 32 bits. With user selectable output formats like raw IQ, binary IQ, or waveform IQ format. This short video demonstrates the easy, simple operation of taking IQ captures and remote controlling the instrument in parallel. You can either set your parameters and transform them onto the device, or you click on Download Capture Setting to download the existing parameters configuration. A right click on the mouse button is starting spectrum and spectrogram view. You can set the capture length, and clicking on Start Data Capture results in an execution of the given parameters, whereby the IQ files are saved onto the remote control device. Because you have initiated load up the capture, you can immediately switch over to replay the recorded signal. You can influence the time resolution of the replay and the replay speed. A marker functionality with maximum to markers allows for doing some frequency-related measurements. This is easy, right? This was the functionality so far of the File tab. Now let's have a look to the View tab. The View tab lets you investigate the captured file in the baseband domain, also called time domain. The replay functionality, as we already have seen, and the possibility to replay up to 4 different IQ files with different time offsets in parallel. Here we see the View tab of the main GUI. The user can display I and Q separately, or draw the magnitude to see power versus time-like behavior. The system allows also for automatic detection of signal characteristics and shows all these instances in a list format in the top right corner. The user can select to display the entire time record length also. Here we see 9 seconds in total. It's easy to recognize 3 very similar signal bursts that we see here. This one, and this one. Besides audible replay of AM, FM is also possible, including raw IQ and CCDF representation. Here again, the Signal Replay tab. Let me mention the possibilities of the time marker table and the power versus time representation. In the following short video sequence, we are presenting in brief the functionality of the View tab. We are loading a file covering a 1-minute period of time and the signal bandwidth of 1.25 MHz. And again, you can easily identify similar burst structures as we see here. Next, we load the same file into the file conversion mode. This is because we want to extract a part of the original file for later physical retransmission on a vector signal generator. Here we see the results. Now we define marker positions, left and right of the burst that we intend to extract. The vertical green lines are indicating the new limits. And then we copy the trimming information into the so-called clipboard. We set trim start and stop and save the new file under a different name. It is also possible to change the parameters in detail, for example, a new center frequency. The final OK is executing the operation. Now let's see the result. We are going back into the View tab and load again the new trimmed signal. As expected, everything went well. Finally, we are replaying the new FSK signal again. A decimation would have been here useful to change also the frequency span. To see this here more in detail. We see here the power versus time tab also that you can operate. So you have seen how easy it was to load an IQ file, to trim the IQ file, and replay the trimmed IQ data again. The analysis step allows us to perform vector signal analysis or to investigate the details of a captured 5G signal. LTE and 5G frame analysis and vector signal analysis. Here today we are not going into the details of the vector signal analysis. We recommend that you are downloading the sample files and following the demonstration instructions in order to get familiar with the meaning of vector signal analysis. We put the conversion tool here at the end. As said beforehand, you can convert between different IQ file formats. You can trim captured IQ data, and you can transfer automatically the IQ files into the waveform memory of Anritsu or Anapico vector signal generators. All the above mentioned features are clothing the measurement and analysis loop. We start by capturing a signal. We might edit the signal and convert it into a waveform pattern file that is automatically forwarded into the waveform memory of a vector signal generator. And we might retransmit on the same or different frequency. So this is the loop of capture, replay, and retransmit. Here we see an interesting chirped radar signal. It is a speed camera that is usually working at 24 GHz and is monitoring up to 3 highway lanes in parallel. The signal was captured, a small portion was trimmed, and is now retransmitted on a new frequency of 2 GHz instead of 24 GHz. IQ post-processing using XCOM SpectreX software. The next chapter is dealing with third-party software tools that allow the operations on the IQ data itself. These features are more advanced and therefore more meant for the professional user. We are introducing here a tool from XCOM that is named SpectreX. It allows for editing, shaping, and replay of IQ data files. The user can filter and shift signals in frequency, and it allows to search for signal content by applying autocorrelation technologies. You can see here on the right side a typical spectrum with overlaid RTSA and a spectrum plot. SpectreX is a visualization, signal search, and measurement tool for analyzing IQ datasets. It allows also the conversion in different formats. The tool is compatible with the IQ data format of the previously introduced spectrum analyzer hardware. SpectreX offers the user a couple of very intuitive tools. Besides signal replay, you can look for specific signal parts in the time and frequency domain. Markers are always permanently visible in all other domains. You can detect signals by looking for amplitudes, you can look for pulse behaviors, and so on. You see here in the so-called summary plot that is always representing the entire time record length. So you can see where the interesting parts of the signal are occurring. Next below is the permanent power versus time plot that you can see here. At the bottom you can see the marker operation menu and the specific marker mathematics tab. Multi-domain processing is always executing all changes in parallel. The user can apply different resolution bandwidths in spectrum, RTSA, or spectrogram plot. It is possible to trim and export parts of the signal, whereby the user can apply also shaping filters and frequency shifts. Let's come back here again to the before presented speed radar signal. By using the spectric features, it is possible to gain parameters like center frequency, chirp bandwidth, chirp duration, and duty cycle, and so on and so on. The analysis bandwidth is dependent on the hardware that delivered the IQ data, not onto the software. A closer look into the RTSA overlay spectrum reveals the sweep start of 24.075 GHz and an effective sweep bandwidth of 83.5 MHz. You can also identify the two different chirp settings visible by the four dominant spectrum occurrences that you see here and here. Now we would like to operate with more advanced features. The so-called waveform search is some kind of autocorrelation. Firstly, you extract some part of a signal. In the second step, you use this extract for autocorrelation measurements. The pulse search feature delivers information about the individual detected pulses, like pulse duration, pulse repetition frequency, and power readouts. Here we see the just mentioned extract. We have isolated a single pulse. You can observe the results in parallel in RTSA overlay, spectrogram, and power versus time. This part of the signal is now exported and used for autocorrelation measurements. The result will inform you how often exactly this signal occurred in the overall time record. Here we see the result. A number of 1,868 chirps have been detected. The carrier frequency is constant, and you can also read out the point in time and the confidence rate of the autocorrelation. Applying the pulse search feature informs us about the observed power, the pulse width, and the pulse repetition interval. Other parameters are also given. Finally, this is a complete analysis of a pulse signal, and the user has all the time the possibility to zoom in, to zoom out in the time domain. You could click here on one of the detected signals and you would immediately get the relevant spectrum plot or time plot. Here we see the replay of the speed radar capture. Increasing the time zoom by a factor of 4 is showing now first time the expected chirp behavior. This video sequence has shortened a little bit to save unnecessary time here in our webinar. Now we are increasing the zoom in by another factor of 4. Here you can see the fast chirp, time up to 22 microseconds from left to right, followed by a 121 microsecond down chirp from right to left. Besides, some ringing is also possible at the chirping turning points. So you have seen how easy it is, how intuitive it is, and what kind of information you can easily gain by IQ post-processing. IQ post-processing using XCOM RF editor software. Over time or based on your project, you might have collected a number of IQ datasets that shall now be combined to create a defined signal scenario. This is a typical application in electronic warfare scenarios, for wireless communication receiver testing, for spectrum management scenarios, and very often for radar warning receiver testing or spoofing and jamming. The XCOM RF editor allows for an intuitive arrangement of several IQ datasets in the time domain to orchestrate a signal scenario. The tool is reading several different IQ dataset formats. It allows you to shorten or to extend time-wise captured signals, apply filters to eliminate unwanted spectrum contributions, and to apply also linear ramp functions that can reduce frequency splatter. This is one of these ramp functions, and here you see that we have cut out this unwanted frequency behavior by applying this filter, and the resulting is visible here. In the following example, we intend to combine three WiMAX signals, each having a time record length of 10 milliseconds, and a primary surveillance radar signal having an original length of 2 milliseconds. This primary surveillance radar signal is extended then from 2 milliseconds up to 90 milliseconds in time, and finally all signals are then combined for a replay. The GUI allows to drag and drop these IQ datasets and to create this way a 100 milliseconds lasting signal scenario. Here we can see the result. The PSR signal on the center frequency surrounded by the WiMAX signals. Excurse about oscilloscope application. I mentioned a very short excursion about the use of an oscilloscope. The scope shows voltage over time. The given plot is again showing our previously ADS-B mode C signal. A zoom in presents more details. It is very easy to operate marker functionalities to measure PD or the PRF. Remember, I mentioned that it might be of interest to check if a phase change happens really at the given point in time in the signal. This point that we are looking for is visualized by the second dotted line from the left. Another DOM is clearly showing the expected behavior as we are seeing here. Be aware that you can calculate based on the measurement also the peak power of the signal. We have here voltage over time at the 50 ohm impedance. MG3710E vector signal generator. The vector signal generator MG3710E is a best-of-class multifunction signal generator with excellent RF and baseband performance. The MG3710E features wideband vector modulation and offers built-in baseband waveform generation with large capacity memory to ensure maximum versatility. Dual RF and dual waveform options enable a single 3010E to output up to 4 independently modulated signals. The MG3710E makes it easy to implement complex test scenarios that would normally require multiple synchronized signal generators. Here we have a real application. Aircraft radar altimeters might get interfered with by close 5G new radios G-Node Bs. The radar receiver input stage is due to historical reasons relatively broadband, and thus far-off broadband noise from adjacent transmissions might enter the receiver. It might be beneficial to simulate and test such RF environments, and thus capture and replay gives you the necessary tools to do so. In this short video sequence, we see a simulation of the received altimeter signal resulting in blocking and saturation, finally, of the radar altimeter receiver. Now we see clear the saturation effects here. RF microwave signal generator MG372X1A with pulse modulation. Signal purity determines quality of measurements in several applications such as radar, transceiver, ADC, DAC, and components testing. The rubidium MG362X1A offers atomic clock frequency stability with an internal rubidium frequency reference option. Alternatively, customers can also get exceptional frequency stability by locking an internal oven-controlled crystal oscillator reference to an external GNSS, for example GPS signal. The exceptional frequency stability makes rubidium an ideal signal generator for metrology and high-speed clock applications. The AM, FM, PM, and pulse modulation capabilities enable the generation of wide range of complex analog modulated signals. But also the simultaneous modulation of AM and FM, FM and PM, or FM and pulse is possible, and that's why it is also possible to generate complex chirp-like waveforms. Wide range of signal simulation capabilities are built into the signal generator for pulsed radar testing. Pulse Doppler radars combine all the benefits of long range and high velocity capability. Pulse Doppler radars use a medium to a high PRF in the range of 3 to 30 kHz, which allows for the detection of either high speed targets or high resolution velocity measurements. Normally, it is one or the other. A radar designed for detecting targets from 0 to Mach 2 does not have a high resolution in speed, whereby a radar designed for high speed velocity measurements does not have a wide range of speeds. That's the catch-22 here. Weather radars are high-resolution velocity radars, while air defense radars have a large range of velocity detection, but the accuracy in velocity is in just the tenths of the knots. There are cases where it is necessary to be able to distinguish between small or very small Doppler shifts. Insufficient signal generator phase noise behavior might shield Doppler shifts that are very close to the carrier. Here, it is essential to have a signal source with premium phase noise behavior. And here in our case, it's again the MG372X1A. In the top left corner, over here, we can see a typical aircraft approaching a radar site. The radial speed is given in red, the tangential one in blue. Now, think about several targets, but being very close to each other in speed, like we see here. The resulting Doppler frequencies are very small compared to the carrier frequency. Phase noise of the local oscillator might shield these small Doppler shifts. Our example shows some typical Doppler shifts calculations for a radar that is operating at 2795 MHz. A radial speed difference of approximately 5 knots is resulting in a Doppler shift of 51 Hz just. This is very small compared to 2795 MHz. Option 3 of the MG signal generator provides a specific low phase noise option and a very high stability. And option 13 is even improving up to an ultra low phase noise. And this is the best in class what the market at the moment is offering. As mentioned beforehand, simultaneous modulation of AM/FM, AM/PM or FM pulse enables complex modulation waveforms such as chirps, but also pulse trains. The intuitive graphical user interface allows easy setting and switching between all possible parameters. It is possible to define pulse trains up to 4 pulses with different pulse widths and timing behaviors to each other. This slide presents the idea behind. The pulse period is set beforehand, and the user can define up to 4 different pulses within the given PRF. You see, that is here the PF period, and within the PRF period, the user has any kind of freedom to define a pulse train consisting out of 4 pulses. For sure, it is possible to apply trigger to waveforms. Standard operations like free running trigger, but also gated, a delayed or an external or internal trigger, or even a compositive trigger is possible here. This final sketch explains the various trigger possibilities and the understanding thereof. Look to this a little bit later in detail if you want. Anapico Vector Signal Generator AppVSG, AppVSG-X. This is our final chapter. And we are closing the webinar talking about a very powerful vector signal generator, especially on the background of radar signal generation. The question is how far the radar applications extend in the frequency spectrum nowadays. Up to which frequency should you be prepared to meet future applications? Here today, we are ignoring industrial radar applications because they are usually beyond the 60 GHz range. The table on the right side shows frequency bands and some typical radar applications. The Ka band covers frequencies in the range from 27 to 40 GHz, equal to a wavelength of 1.1 to 0.75 centimeters. Based on the IEEE radar band frequency designations, this Ka band showcases high potential in supporting high resolution, close range targeting radars, military aircraft radars, space telescopes, commercial wireless point-to-point microwave communication systems, vehicle speed detection systems, and also satellite communications. Thus, for the future, you need to be prepared up to 40 GHz so far. There are several enabling factors that qualify a VSG for radar applications. Some are listed here. A small form factor for the lab bench is important, but at the same time, multi-channel capabilities and rack mounting might also be required. As agile radar is dealing with speed, it is required to provide fast frequency switching capabilities. We have already heard about phase noise in previous slides. A VSG has slightly worse phase noise performance compared to a synthesizer. However, challenging specifications require performances beyond the minus 110 dBc for Ka band applications. In part 1 of our webinar, we have discussed pulse compression techniques. We heard about the so-called chirp bandwidths. In practice, we see typical chirp bandwidths from some hundreds of kilohertz to some tens of megahertz. These are real-world chirps. In industrial applications or automotive applications, the chirps have a much wider bandwidth. For example, in the automotive radar world, the chirps are going up to 4 gigahertz in contrast. In other words, a 400 megahertz IQ bandwidth of a VSG will cover very well nearly any radar application in the market. A large waveform memory is important for longer replay pattern. Radar PD and PRI patterns might be long and repetitive. On this background, it is very beneficial to avoid memory-intensive IQ waveform pattern and use instead so-called pulse descriptor words. We are talking about this in more depth in the next couple of slides. The Anapico App VSG platform fulfills all mentioned features. Different frequency models, different form factors, coherent multi-channel and several scaling options qualify this device as an ideal tool for radar signal generation. So, what are now pulse descriptor words? Think about a comma-separated file format with several columns that contain relevant data to describe a pulse, like pulse duration, pulse repetition frequency, pulse power, timing, etc., etc. Each line of the CSV file represents a so-called pulse descriptor word, also called PDW. A list of PDWs will fully describe a radar pulse stream over time. Here on the right side, we see a typical content. A single pulse can be described by 255 different parameters in total. You can see descriptions of the carrier frequency and power as well as modulation and timing parameters. Here now we see a real-world extract of such a CSV file. You can imagine the benefit of loading such simple pulse descriptions into the VSG or even streaming such ASCII-based parameters. A pulse descriptor word can not generate a modulation in the classical sense, for example, a QAM16 modulation. But the PDW can be seen as a high-level interpreter to generate a single pulse or longer pulse trains. The opposite is also possible. We are not going here into the details. PDW can not only be used to create a radar pulse, it is also possible to convert the received signal in IQ automatically into a pulse descriptor words or a list of PDWs. Even several parallel radar signals can be de-interleaved into different PDWs with the right use of software. Such techniques are used in electronic warfare applications today. The app VSG provides two different pulse descriptor word operation modes. The first, the so-called sequential playback, where several pre-compiled PDWs are uploaded into the device memory via local area network. The operation of multiple channels is also possible here. Second, the PDW live streaming, where parameters are streamed via the fast control port, the so-called FCP, directly into the memory for playback. The instrument provides a buffer of 1024 PDWs. It is possible to save and playback up to 65,000 Pulse Descriptor words in a list mode. It is possible to create time spans as large as 208 days. Let's talk about some definitions. First, phase continuity and discontinuity. A signal is phase continuous if after switching frequency, the phase of the signal is the same as before the switch occurred. If the phase changes after switching, the signal is phase discontinuous. Second, phase coherence between two channels. If the phase relationship between two signals remains constant, the signals are considered to be phase coherent. Third, phase coherent switching. Phase coherent switching defines the state of the signal's phase once frequency switching is complete. Two signals at frequency f and with relative phase phi are said to be phase coherently switched if the relative phase is again phi whenever they go back to frequency f2 or f1. Phase coherent switching in multi-channel mode guarantees deterministic and reproducible phase relationships between multiple individual channels across multiple individual VSG units. Phase coherent switching in multi-device mode also enables synchronous playback of IQ waveforms on multiple channels and multiple devices. Here we see a real example. The relative phase between channels 1 and channel 2 remains the same after channel 2 temporarily switched to a different frequency. Phase memory. A signal phase memory, or a signal has phase memory, if, when switched from frequency f1 to frequency f2, and then back to frequency f1, the signal's phase is the same as if it had run continuously at frequency f1. Here we see another real example. The signal returns to the same absolute phase when returning to the previous frequency and amplitude setting. With option PHS, the app VSG guarantees deterministic and reproducible phase relationship between individual channels and individual devices. Deterministic and reproducible, however, mean that those relationships may still vary with power and frequency settings. Varying RF pass configurations, like gain and attenuation settings, might cause jumps in the phase relationship over power and frequency settings. Therefore, phase calibration is only feasible for selected combinations of power and frequency. Covering a broader range of power and frequency would require a very high number of phase calibration points, causing prohibitively long calibration measurement times. The phase calibratable operation mode, also called PCM, addresses that shortcoming by using less and therefore larger ranges over power and frequency using a common RF pass configuration and therefore generating stable phase relationships. Power setting accuracy and resolution is maintained by scaling IQ modulation data instead of adjusting RF path gain or attenuation. To make the long story short, there are three possibilities to operate the phase correction and the phase calibratable mode. First, off-off. This is a default operation mode. Channel-to-channel relative phases are stable and repeatable, but not zero, and show variations over power and frequency. Second, phase correction off and phase calibration mode on. This mode enables linear relative phase variation over frequency and static phase over power. Channel-to-channel relative phases are stable and repeatable, but not zero. Third, phase correction on and phase calibratable mode on also. Correction values are interpolated between points. This enables true zero phase offset between channels over any frequency or power range, up to a device full power and frequency range. Thanks and goodbye. Many thanks for being with us and listening to our Radar TechDay webcast. This was a lot of different stuff. The intention was to give you an overview about the different measurement possibilities offered by various instruments. It would be great to meet up with you in person to discuss your individual applications. I'm convinced that Anritsu will be able to offer a solution for your test and measurement requirement. Thank you for watching, thank you for listening, and goodbye.